right. We should be seated.
All right. So welcome everyone who is here in person, and welcome everyone online. I'm not really sure where to look. Is there a camera? Oh. Hello. Yeah, so welcome. We've put on a number of events today. This is Hassan is going to be kicking us off. I'll introduce him in a moment. But after this, there's going to be lunch for those of you who registered for that. Maybe we'll have a few extra in case you've just snuck in. We are also going to hear about updates on computing, which are very exciting in the cluster. And then we're going to have two T-Talks later on, which is a tradition we're going to hope to get started here at Vector to have kind of regular short talks, low stress, and create some more social mixing here. Right. So I'll now introduce our speaker, Dr. Hassan Ashtiani. He comes from us from McMaster. He's a Vector faculty affiliate. He got his PhD in 2018 from the University of Waterloo, working with Shai Ben David. Hassan is highly decorated, having won the NERV's Best Paper Award fairly recently, and he's well known for his work studying learning under constraints like differential privacy or under model misspecification, a variety of work, all of it very deep. So we're going to hear more about some of that work today. So thank you for coming.
Thanks. Thank you for the nice introduction, man. Thanks, Jackie, Sylvia, help with arranging the talk. So I'm going to talk. Let me try to see if I can see the slides from there. That would be easier. For now, it's good. Okay. So let's see. So today I'm going to talk about differentially private learning of distributions. So I'm going to define differential privacy and things like that, but you already probably have heard about differential privacy if you haven't worked on it. And this is a screenshot of a few archived yesterday, and there are many papers on differential privacy. You see differentially private XXX, like anything that you would do in machine learning, there's a differentially private version of it potentially. And so it's a good opportunity to design various algorithms and make them private. But what is this talk about? We will talk about one ambitious goal. And let's say you have one machine learning algorithm that you think it's a good algorithm, it works well, and you have perhaps some guarantees for it. It's not private in some sense. Can you take this algorithm and make it private in the sense that you want to design a differentially private version of this algorithm by only accessing the data through this non-private algorithm? If you can do that as a black box, like use the non-private algorithm as a black box, then it will be very useful and you can make all sorts of non-private algorithms private. But can we do that? So we'll get back to this. But before that, let's start with some background about differential privacy, especially in case you haven't digged into it before. Consider these problems. Let's say I want to train an LLM on the emails data so that it can help you, for example, with auto-completing your emails. Obviously, this is an important matter, and privacy here is very important. So you don't want to create some privacy issues. Other tasks are training a classifier on, let's say, medical records. So it's very important to have accurate classifier for medical applications. At the same time, you don't want to violate privacy. Other examples are releasing some statistics about communities. You want to make sure they receive good resources, but at the same time, you don't want to reveal the identity of, for example, people that have participated in the census. And finally, you want to publish some data set for for encouraging research on this topic, but again, you have some privacy concerns. Can you do that in a private manner or to make sure that you keep individuals' information private? So I like this example of Netflix challenge. You may have heard about it before. In 2006, Netflix started a competition with $1 million prize. And the task was to, like they have a recommender system, they wanted to predict, based on the users' reviews of the previous movies, we want to predict which other movies they like. And they had a baseline themselves, and they said, if you improve 10% over this, you will get the $1 million prize. So for a few years, it was not 10% until 2009, where a couple of teams became so close to 10%, and then they started to merge with each other. So the team, like 3 top teams, they said, let's merge our classifiers, create an ensemble, and then they went above 10%. And then once other people saw that this is happening, they all merged together and created another team, and they also got 10%. So it came to the last minute. They eventually had the exact same accuracy on the held out data set. So there was a tie, but because one team sent 10 to 20 minutes earlier the submission, they won the $1 million. Okay, so but that was there was a question, or it was me? This was not the concerns that we are talking about. In 2007 and 8, there's a little bit of echo, it seems.
If everyone can make sure they're muted, that would help.
We post to force me.
There, okay.
Yes.
Okay.
So in 2007 and 8, there were some privacy attacks on this data set. So the data set was released in an anonymized way. You didn't see the names of people who had rated the movies, but still people figured out how to kind of reveal the identity of many of the participants in the data set. So and there was a class action lawsuit, and the competition was closed afterwards, canceled. So how did the attack succeed? So here you see that although the data set is anonymized, many users in the data set have rated many movies. So you can't, it's quite small in here, but you can see that many users have rated more than 100 movies. And if you think about it, this is a lot. And furthermore, many users have kind of a unique taste. Again, this is pretty small here, but for most users, the most similar other users in the data set is pretty far from them. Like for many users, their taste is quite unique, and therefore it's kind of like a signature for that user that you can understand who that person was. So this is already bad because it kind of shows who participated in the data set, but there was another aspect to it. We have the public IMDb data set, sorry, not data set, the website, and there people have rated many movies. For example, I just looked at this user, randomly found this user 500 total reviews. And if you match this user's reviews with the reviews in the Netflix dataset, you just find one particular person with such a unique signature. So it helps you to connect these two data sets and figure out other movies that that person, that public figure has watched and rated, which obviously is not good, especially if it's a movie that they didn't want to declare they have watched on Netflix. Okay, so what was the issue here? What happened? So one issue was that when Netflix released the information, they anonymized it. So the private information was obscured somehow or hidden, but not completely undetectable. It was detectable. And it came to light when we had another source of information or side information, which was IMDb. So how can we make sure that this doesn't happen? So maybe if Netflix people had looked at the data more carefully and looked at these data points, they would have thought about this and figured out something. But this kind of approach to try and predict what the attacker does and defend against it is not reliable, because you cannot really predict what they are going to do. You need a more systematic approach to preserve privacy. So the question is that can we have a more rigorous way of defining privacy that can be applied in a variety of applications? And that's where differential privacy is useful. So look at this figure. You have two data sets, and each data set consists of records of various individuals. These two particular data sets differ in only one data point. We call them neighboring data sets. Differential privacy requires the outcomes of the algorithm on these two neighboring data sets to be almost identical. What do I mean by that? They should be statistically indistinguishable. The algorithm must be randomized, first of all, and the probability distribution of the algorithm in these two cases should be very close, so much that if you get samples from these two distributions, you wouldn't be able to easily say which distribution was the case. So why does this make sense? Because we want the contribution of each individual, like this person that we added to the data set, to be undetectable, and this person will have some deniable, plausible deniability. Okay, so I said the two distributions have to be statistically indistinguishable. The details don't matter, but if you work in this field, the definition that we use is epsilon delta, or approximate differential privacy. That's a definition between a distance or divergence between two distributions, and defines when we say they are indistinguishable. Okay, so let's get back to the original question. Consider a learning task such as classification or distribution learning. And we know we have a good algorithm for non-privately solving this task. Can we make it private? More specifically, can we have a computationally efficient and also a statistically efficient black box reduction from the private version to the non-private version, so that we just use the non-private as a black box and solve the private version of the problem? So the answer is not always positive. For example, consider the task of linear event classification on a continuous real line, for example. It is known that you cannot learn a classifier, even linear classifier, on a real line in a private setting, but you can do it in the non-private setting, which means that you cannot simply take a non-private learner and make it private, because we even know that it is impossible to learn a linear classifier. So what are we looking for then? There are two things that we are looking for. First, can we assume something extra about the non-private learner? For example, maybe some sort of stability. And under that assumption, show how to make it private. That's the first question. And the second question is that maybe for classification, we have this situation. Maybe for other tasks like distribution learning, we can actually come up with a very general black box reduction. So let me talk about distribution learning, which is the set of tasks that we will talk about, we will focus on in this talk. So let's say you have a class of distributions. for example, Gaussian distributions or Gaussian mixture distributions, etc. You have some IID samples from one of the distributions in this class, and you want to recover or approximately recover the distribution that generated the data. It's a very generic unsupervised learning task. If we want to, for a second, be a little bit more formal, this is the definition. It's not sure if you can see it properly, but we say that an algorithm A learns a class F with accuracy alpha using n samples if for whatever the underlying distribution is, the probability, if we generate m samples from the distribution and give it to the learning algorithm, so the learning algorithm outputs f hat, and the true distribution is f, we want some kind of distance between the actual distribution and what the algorithm outputted to be smaller than alpha with high probability. So that is the more formal version of this distribution learning problem. And again, you have many choices for the classes of distributions, for example, Gaussian distributions, mixture of Gaussian, etc., or even generative models. And we have different choices for the distance function. It could be total variation distance, it could be parameter distance, some kind of distance between the densities, etc. And we have different requirements for the algorithm. For example, we may be interested in reducing the number of samples it uses. We may be interested in making it robust to some outliers. We may be interested in making it private or computationally efficient. So it's a good playground for seeing whether this general idea of private to non-private reduction works or not. So it's a rich playground. Okay, so how can we possibly create such a reduction? One idea, which is the most natural idea, is to use some kind of sample and aggregate scheme. What do I mean by that? So let's say you have a data set that you want to make it keep it private, and you want to, based on it, train or find the distribution that is generating the data. You divide the data set into disjoint subsets. You run the non-private algorithm on each of these subsets. You will have multiple outcomes of non-private algorithm. And then hopefully you are able to privately aggregate this information. So the hope is that because the non-private algorithm is supposed to work, all these non-private solutions are kind of close to each other, because if not, then even the non-private algorithm does not work in a sense. So because all of these are close together, maybe it's easier to aggregate these privately aggregate these close solutions. Okay, if we can do that, it will have multiple benefits. One benefit is that the private algorithm will be probably simple because we have encapsulated or abstracted away the complications of the non-private algorithm. Maybe the non-private learner is super complicated, but we just run it as a black box, so we don't need to deal with those complications. The second benefit is that you can simply replace your non-private learning algorithm with some other non-private learning algorithm, and maybe you will get a better result without really changing anything. So it's very reusable. Another thing is that if you are writing a code that for a differentially private algorithm, you should be very careful, because maybe you make a mistake in one line of code and leak some private information of the individual. So you need to maybe write your code in a more encapsulated way. So this reduction, using things as a black box, helps us to avoid those mistakes, because your non-private algorithm can do whatever it wants with the data. It's fine. Still, the information will remain private, even if there is a bug in the non-private algorithm. And another thing is that the non-private algorithm has access to the raw data, very private data. So intuitively, that will help the performance of the non-private algorithm to be good, especially in the sense that if the data has some nice properties, then we expect that the non-private algorithm to also work better than what the worst case suggests. And still, we can privatize these and exploit this niceness of that. Any questions so far about differential privacy? So from this point, we want to be a little bit more concrete, and we will start with one such approach, some sample and aggregate approach that actually works in some applications. And it's about a notion called global stability. I'll define it in a moment, but if you can find a non-private algorithm that it has an extra property that is globally stable, then you can make it private. So what is a globally stable algorithm? So here we have M and rho globally stable algorithm A. So for every distribution of the data that you pick, every D, there exists one good hypothesis or solution that depends on this distribution. Let's call it HD. That if you run your algorithm on a new fresh sample of size M, then with some good probability, with probability at least rho, this algorithm will actually exactly output this hypothesis. Okay, what does that mean? More intuitively, it means that, let's say you divide your data set into chunks. You run this non-private algorithm A on each chunk. It is telling us that some of these results will be exactly identical because it's globally stable. With some probability, let's say rho percent of these answers are exactly the same. And this is very helpful if you know about, for example, private histograms. You can just apply private histograms after this. But even if you don't know that, it's easy to see that because there are many outcomes that are exactly the same, it's easier to hide information. So any globally stable algorithm can be privatized. So there are two important examples here. One is about classification. So I said before that you cannot develop a private algorithm for learning linear classifiers even. But which classes of functions are learnable then under privacy? We actually know the answer. Exactly those classes that are called Littlestone classes. It doesn't matter at this point which classes are learnable. The thing is that any class that is learnable in the private setting can be learned with a globally stable algorithm. So you can always, some classes are not privately learnable, we don't care about those. If it is privately learnable, then there is some algorithm A that if you run it on multiple disjoint subsets of data, it will output the exact same answer on multiple data sets. And then you can easily privatize. And yes?
So it's this observation that globally stable algorithms can be easily privatized, inclusion of the stuff that provides on the wrong, but or is it your result?
No, this is for this paper, and really this is the paper that defines globally stable algorithms, but really it comes from previous approaches. They implicitly use similar ideas, even in 2013. Yes.
What is the relationship with this one I mentioned?
Oh, the littlest of. So if in a few sentences, if a class is littlest known, then there is an online learner. And because there is an online learner, you can globally learn it in a globally stable way because if you're making only a few mistakes, then you're not changing your hypothesis a lot. Yes.
What was the bound, the lower bound that you showed that you just quickly asked? So just previous, yeah, if you click back, yeah. So what is that bound that you?
Oh, it's not a lower bound. Maybe my notation is not good. I meant if this probability of repeating the same answer is rho, then you kind of need 1 over rho many subsamples so that you get some kind of repetition. You want to run it on multiple disjoint subsets until you see multiple repetitions, then it becomes easy to privatize. Yes. So actually about this older result, there is a much easier setting that globally stable algorithms are possible when your outcomes are, the number of solutions is very small. Maybe if you have heard about, for example, hypothesis testing or something like that, you have 10 possible hypotheses, you want to choose one of them. And because you only have 10 options, you are kind of already globally stable because with some probability you will output the same answer. So in discrete settings, it was known this is the new classification set. Okay, so let's see an example for a distribution learning problem. And the easiest distribution learning problem is learning a univariate Gaussian distribution. So these are not data points from a Gaussian. So let's say I divide my data set again into disjoint parts. I want to estimate the mean of the Gaussian, right? So I have a very easy non-private algorithm to just take the empirical average of the data points and report it as a mean. This is a very naive non-private estimator. So these orange points are the outcomes of the non-private estimator or different subsets of data. So as you can see, the outcomes are never identical. They're very close maybe, but it's not globally stable in that sense. But this is not an issue. Maybe you can just discretize the domain and change your non-private estimator to slightly discretize these outcomes before releasing them. Then you will have a globally stable algorithm with some probability it will output the exact same answer. So you can do mean estimation on a univariate Gaussian easily using a globally stable algorithm. What about in high dimensions? Okay, now this is not so simple anymore. Because let's say your actual mean is on the boundary of multiple cells in your discretized domain. Then there are exponentially many cells that are close to it, and every time you run it, it may end up in one of those. So you don't get really repetitions, and you cannot use it unless you have exponentially many samples. So this approach does not work in high dimensions. You cannot have globally stable algorithms. We'll see a relaxation of this definition that works. Okay, so today I'm going to talk about 3 different works, kind of from easier to harder. And all of these are based on some kind of subsample and aggregate scheme. Okay, let me start with the first approach for learning just Gaussian distributions. So what kind of, let's say you have a Gaussian distribution, you don't know the mean, you don't know the covariance matrix of this Gaussian distribution. You only have data points and you want to estimate it. Estimate it in which distance? The L1 distance, which is the kind of integration of the area in between your estimate and the true Gaussian. You want to minimize that. The question is that how do you do it efficiently, privately, and hopefully even robustly? So robust setting is like, you know, that the median is a robust estimator for in the one-dimensional case. In high-dimensional setting, being robust to outliers is not easy at all, and there are more sophisticated algorithms that can do that. So can we take these easy or sophisticated algorithm as a black box and make it private? Okay, so there's a long, like there are a couple of papers on this topic, but I'll talk about this work that is our work about subsample and aggregate scheme. So you run, again, you divide the data set into disjoint subsets. You run the non-private algorithm, estimate the Gaussian using each subset. Each blue point here is one non-private answer. So maybe a few times it doesn't work well, the non-private algorithm, but most often it is supposed to actually work. So the solutions are supposed to be close to each other if we think that the non-private algorithm is good. So we privately check if these solutions are mostly concentrated. Otherwise, we reject and we output some trivial answer. Then we remove a few outliers, take a weighted average of the rest, and add some kind of noise so that it kind of mixes all these things together and they become undetectable from each other. The main technical point is that how to add noise. Let me mention that there's another approach similar to this that can be used. But the challenge of adding noise is that you cannot simply, for example, let's say you have estimated the mean, and then you want to add some kind of noise that makes it undetectable from the neighboring data sets. So you cannot simply add Gaussian noise. The reason is that if your Gaussian distribution has a covariance matrix with high condition number, then your noise should also scale with that. Otherwise, it will ruin your accuracy. But at the same time, this is a private information, like you don't know where the covariance itself is. So it makes it a little bit more challenging. Anyway, so we figured that there is a way to scale the Gaussian distribution, a spherical Gaussian with some estimated covariance matrix, and it will still work. Okay, so the thing about this reduction, yes?
Yeah, sorry, the scaling, is the estimation happening on private data as well?
Yes. You mean
Like those, yes.
this sigma is the empirical, yes. So let me go back to. So I said that we will have a green weighted kind of aggregation that we want to add noise to it. So that sigma is the covariance of this green Gaussian.
And one other question, the terms that privately check and otherwise essentially reject. So like, because that also consumes privacy budget, right? Like, can you give a relative estimate of how much those rejection cost you relative to?
Of course, so the question is that the third step, which is checking whether most solutions are close to each other, how much of privacy budget it uses, it's actually negligible compared to the other steps. The reason is that we have something called proposed test release, and it's kind of just one real valued number that you want to say, if I want to give an intuitive answer, we will somehow, for each blue solution, we count how many of other solutions are close to it. If 90% of other points are close to a blue point, is kind of a non-outlier point. And if most of the points in the data set are not outlier, then we don't want to reject. So we kind of average these real values. So it's not a high dimensional problem. So just a univariate estimation problem of concentration. So that's why it's easy compared to this, which is more problematic. Yes.
So if this is a univariate,
This,
Right.
no, the whole approach is not univariate.
okay, so still this global sensitivity on differential privacy would be D over N, depending on the number of dimensions, right? So if you make that estimation, so it's still that, so how is that?
Yes,
Once
it's the
again, how
question.
it's related to the global sensitivity in differential privacy? Which is that sensitivity is fixed for multivariate Gaussian, right?
Yes. So the question is that, let me rephrase your question. Why can't we just use Gaussian mechanism? Because we know that it's a standard differential private algorithm with good sensitivity, etc. That one intuitive answer is that the covariance matrix, like the distance with respect to which we want to learn the distribution is a L1 distance. So even if you add a tiny bit of Gaussian noise, you can ruin your estimation. Let's say your Gaussian distribution has a very high condition number. Let me draw it here. So let's say this is your Gaussian distribution with a high condition number. So if you add a little bit of just noise to this, isotropic noise, you may end up moving this distribution a little bit towards down, which introduces a lot of error. Now these two Gaussians do not even overlap. So the L1 distance is high. Yes.
To compute your eta, you need to do the definition number of the variance or the eigenvalues.
Eta, let me see.
The next slide.
Oh, this one.
Yeah.
Yes, so eta depends on the privacy parameters as well, right? So if we, like intuitively, the more eta is, the more noise we are adding to the covariance. So it depends on both dimension and epsilon, like your privacy budget. So intuitively, 0 eta means that you just have sigma, square root of sigma times the square root of sigma, just sigma itself. So no noise. If eta is very large, you will have all noise. Okay. So the benefit of this approach is that it's also computationally efficient. Okay, let me briefly talk about the second application, which is about parameter estimation for GMMs. So what is a GMM? A Gaussian mixture is the PDF of a Gaussian mixture is like multiple Gaussians that are mixed together. On the right side, you have a spherical mixture Gaussian. Each covariance matrix for each component is diagonal. And also on this one, not only diagonal, but kind of like identity matrix or a multiple of it. And this one is a more general Gaussian mixture. So what do we mean by parameter estimation? Let's say you have an algorithm that receives the data points and outputs a set of mean, covariances, and weights for each of the components, right? And you want these to be accurate. What is the definition of accuracy here? You want the weights that you estimate to be close to each other. Also, each component that you estimate, each Gaussian, you want it to be similar to the actual component. But up to a permutation, because if you change the order of the components, it doesn't matter. So let's call this definition the distance of parameters, d param. Okay. In order to do parameter estimation, you need additional kind of separation assumptions. If your components are all on top of each other, you cannot reliably even estimate with a lot of samples which component, you cannot recover the component. So we have some assumptions to make the problem identifiable. For example, the Gaussians should not be very close to components and the weights should be larger than some minimum number. So we have two important results in this area about in the non-private setting. The first one is the Moitra-Valiant result that says consider GMMs with those minimal identifiability assumptions that we made in the previous slide. Then there exists an algorithm that to learn this class of mixtures efficiently, learn the parameters efficiently with respect to the dimension. So it's polynomial in the dimension, but exponential in the number of components. So it's not ideal, but that's the best we can hope for because this is unavoidable. You cannot do better than exponential here in the number of components because there could be multiple Gaussians that are mixed together and then they look like one Gaussian and there's no way for you to detect them unless you have many samples. There is a second result. This one makes a little bit a stronger assumption. It assumes that the mean of the Gaussians are spherical and the means are a bit further away from each other. Log of the number of components is the separation between the means. Then under this additional assumption, you can actually have an algorithm that is polynomial both in the number of dimensions and in the number of components. Okay, so these are complicated algorithms. Maybe we can try to create a private version of these, but that will be very tough. Like if you look at, for example, in the second approach that I talked about, there's a long history of many algorithms that are super complicated. And so it's not easy to make them private. So instead, we want to take them as a black box and again, make them private. So it turns out that a similar approach that we use for the Gaussians works here too. You just divide the data set into multiple subsets, run the non-private estimator on each part. You will receive multiple GMMs. These GMMs are close in the parameter distance. In other words, every component of them are close to each other. That was the definition of parameter distance. Now you can check, again, privately check if they're close to each other, and then remove outliers and add noise to all the components, both the means and covariances and the weights. Okay, so there are a couple of maybe small issues that you need to be careful about the order of the components, and you need to shuffle the components, but maybe we can skip that. But the take-home message is that you can have now a polytime reduction from private to non-private for GMM parameter estimation. Okay, so let's.
So there's no additional assumption there. Every one of these GMM parameter estimators can be a black box.
As far as I can think of, yeah. Because we don't make any additional separation assumptions or anything. And maybe it's a good point to emphasize that the reason that this is possible is that this is parameter estimation. So in the next problem of density estimation, things are much tougher. Mohammed is here, so I'm going to briefly talk about these two works with him. On one of them, the second one is not published yet, or hopefully it will be on archive very soon. And they're about non-robust and robust versions of this problem. Okay, so let me first talk about the non-private setting. What do we know? So we know that you can, without any assumptions on the GMM, you can estimate its density. With how many samples? Like K is the number of components, D is the dimension, it's KD squared, which makes sense. And there is a big open question whether there exists a polytime algorithm to do this job. And another question is that how to make it private. Okay, in a polynomial time or polynomial sample, sorry. Time, even non-privately, we don't know how to do it. So what is the challenge? Why is it so much harder than parameter estimation? So we said that we have some kind of identifiability issue for GMMs. If the parameters, if the components are close to each other, or then there are multiple ways to represent basically the same Gaussian mixture. For example, you can represent this with one Gaussian or a mixture of multiple Gaussians. So why is it problematic? So when you run the non-private learning algorithm, it will output it may output each of these representations. You are not sure which one. And these representations, when you look at the parameters, they're completely different. Although together, when they mix, they become close. So is there a way to simply make it stable? It's not so simple because you know at least parameter estimation is impossible with polynomial number of samples, right? So you cannot simply say, maybe I can learn the parameters and then it becomes stable. You cannot do that. So here we go back to our original definition of global stability, and we want to relax it in a way that works for this problem. Okay, so here we have the definition of a stable list decoding from that second paper. So here we have an additional parameter, so M, rho, and L. Here our algorithm, instead of outputting the non-private algorithm, instead of outputting one answer, it outputs a list of answers. Okay. The size of the list is L. M is the number of samples that we feed to the non-private algorithm, and rho is the similar parameter to global stability. So we say this algorithm is a stable list decoder if for every distribution on the input, there exists one, again, good hypothesis, HD, that with high probability, it's inside this list. So the algorithm does not have to output like one answer and then it's always correct, like a stable. It outputs many things, maybe many of them are not stable, but there should be one common kind of denominator in all of these answers. We'll see one example in the next slide. But if we can do that, if we can come up with a stable list decoder, then we show that you can learn that class. So this is a very rough bound, but the number of samples depends logarithmically on L. That's the point. That becomes more clear in the next slide. So it will depend on the sample complexity, or M, of the non-private list decoder and the log of the size of the list. Okay, so let's see an example. So we said that even for learning high-dimensional Gaussians or mean estimation, you cannot have a globally stable algorithm without that issue of exponential dependence on the dimension, right? So no globally stable algorithm can have useful property in high dimensions. But the stable list decoding is easy. Why is that? So here we said that you run the non-private algorithm each time it ends up in a close by cell. There are exponentially many cells that it can end up. But the thing is that you can output this whole list. And then you have exponentially many outcomes, but it's fine because we have logarithmic dependence on n. Okay, so what we showed, this is again technical part, that we show that GMMs, you can learn GMMs in a stable way, like you can stably list decode them, and then based on that theorem, we can learn them privately. Maybe one point is that this is somewhat surprising because in this kind of stability is still you need to output the exact same answer. Although there is a list, but it's the exact same answer in those lists. Okay. And one last result is the robust version of this. So what is the, yes?
Can you say a little bit more what just said? Like, how come this is the exact same answer?
So you can kind of create some kind of cover, you can think of it that way. And then because of that cover, you have the exact same representatives for that cover.
Makes me wonder, like, is there a notion of, when you have a cover, of sort of the dimensionality of that cover, like, pick an element of the cover, then what are the elements that are, how many elements are nearby it? It seems like an
Yes. So that's a very good point. So in our first paper, we were thinking, like we were presenting our results in that way. In which way? We looked at the doubling dimension of some space or something like that. We said, I'm creating a cover, and then what is the dimension of this space? And based on that, let's say it's d dimensions, then you have 2 to the d many neighbor cells that the point can end up in, the doubling dimension. So everything was about this dimension. But then we figured out that we can abstract away all those details with just this definition because already L, the size of the list, kind of encapsulates 2 to the d. So you don't need to define it anymore. You just need to say, I have outputted list. It's kind of more general notion.
Yeah.
So
Yes.
probably the size of L is a fixed size that you consider prior to?
So we usually choose L based on what we think works. For example, usually I would say log of L is in the same order as M or something like that. But
Because that will impact the coverage, right?
so if you pick, I would say, let's say you want to design an algorithm, for example, for GMMs, right? So you have a non-private algorithm first. You have some guarantee from the non-private algorithm, and then you want to choose L, right? So I would say maybe one good intuition is what Dan was alluding to. It's 2 to the dimension, because otherwise if it's smaller than that, then it will not have enough to, we will see repetitions. Okay. Maybe I will just mention this without going into the details, that there is a robust version of this, and it's much more surprising to have a stable, robust algorithm, because when you have robustness, your data points are corrupted. So it's very hard to make an algorithm robust if its input is very noisy. But still, we show that we can somehow make it robust. Okay, let's summarize. So we talked about some kind of black box reduction from private to non-private estimation via some sort of private aggregation. One notion was globally stable algorithms, not our notion, but it didn't work well for high dimension. The other approach that we use for Gaussians and GMM parameter estimation was based on this multi-step, like the one that we removed the outliers and added noise. It was computationally efficient. Maybe one drawback was that we had to design the noise. We didn't know how to design the noise. It was not super general. The last approach was based on stable list decoding, which was perhaps the most general approach. You just need to make sure you have a stable algorithm. You don't need to specify any kind of noise. So what are some of the future directions? One big open question is that so in classification, there are classes that are learnable, but not privately learnable. Do we have such a class for distribution learning? We still don't know. So maybe any class that is learnable non-privately is also learnable privately. We don't know that. There is a partial answer that there is some kind of difference between privacy and non-private algorithm, non-private setting, but it doesn't answer the whole question, but check this out. Also, now if we add additional assumption that this class is robustly learnable in the non-private setting, maybe it makes it even easier to show that it is privately learnable. Why do I say that? Because in the parameter estimation setting, it has been established, but not for density estimation. Another maybe a smaller question is that, do we have any class that we can learn non-privately, but we cannot just simply use the stable list decoding that we talked today? So does it always work, or is there a problem that we cannot use it, learn it with a stable list decoding? Thank you.
Maybe one question? For pretty time. No? I guess I have a question. So when you talk about density estimate, you're always talking about L1s. It's a lot of divergences out there, like KL would be another, Hellinger would be another. I mean, do you know if any of these stories change in those settings? I mean, you expect similar answers?
I think with Mohammed, we one time realized that, Hellinger, there could be different answer, obviously, depending. Like Hellinger is more like L1 or L2. I wouldn't, if I want to guess, I would say that still there are some challenges. Like it's not easy to easily say what happens. But for KL divergence, you might be able to show that if you can learn with respect to KL non-privately, you can also learn it privately. I think what we showed was not this, was a weaker version. Correct me if I'm wrong. So if we learn a class in non-privately in KL, then privately you can learn it in TV, we didn't show KL. But I think the story can change.
Right. Well, let's thank our speaker again. Thank you.